Thank you so much. Okay. Thank you so much, George, for the really nice introduction, and thank you for inviting me to participate in your seminar series. It's a true honor. So let's start. Here I have an outline of what I would like to cover today. A very short introduction on the CO basics and what we knew before satellites. Then I will start talking about the Terra MOPITT instrument, which is, I work for MOPITT instrument. I will explain how it works, what it measures, how we validate the data set, how it's evolved through the years, how it complements other satellite instruments measuring carbon monoxide, and so on. I will present some study cases of CO from fires, from volcanic eruptions, city emissions, analysis of trends a long time, and examples of CO simulations, and then a little bit of about the future of CO. First, the basics. Carbon monoxide is an important gas both for air quality and climate studies. As you probably all know, the lifetime of this gas is around 9 weeks. So it's an ideal tracer to identify emission sources, to follow polluted plumes, and to calculate emissions. Its main sources are oxidation of hydrocarbons, biomass burning, fossil fuel burning, and biogenic emissions from vegetation and from the ocean. Its main sink is OH, and because of that, it determines the concentrations of OH, and that's very relevant for the life of other species in the troposphere. CO is a precursor to CO2 and to ozone in the troposphere. It has a modest radiative forcing of around 0.2 watts per square meter. And it's important to have global CO measurements to evaluate atmospheric chemistry models, transport models, to improve emission inventories, and so on. And a little bit about what we knew before satellites. So let's move all the way back to the 13th century, when this gentleman here called Arnaud de Villanova, he may have been the first one to ever describe carbon monoxide, although evidently he didn't call it this way. He wrote about a gas produced, a lethal gas, toxic gas, produced from the incomplete combustion of wood. And I have to tell you this story, which I learned very recently, because he was born a couple of kilometers south of my own hometown, so I had to just tell you. Now, if we move on for 500 years or so, we get to Joseph Priestley, who was the first to realize that the air is not one single matter, but it's the combination of different gases, which he didn't call gases, he called airs. So one of these airs was heavy, inflammable air, which is carbon monoxide. Of course, he also described oxygen and SO2 and CO2 and many other things. Now, if we move to the 20th century, Millot, doing laboratory measurements with an instrument like this one here, detected in the atmosphere the presence of carbon monoxide, and also he realized that measurements done in consecutive days showed different concentrations of CO. Later on, in this paper from 1973, Seiler presented a compilation of measurements done mostly from ships. And in this graphic here, we have latitude between south 60 and north 60. And you can see that the compilation of measurements show very nicely the difference between the northern and southern hemisphere. In the northern hemisphere, concentrations of CO are bigger than in the southern hemisphere. In this paper, he describes many other very interesting things, like he talks about measurements done from Lufthansa planes, and he notices that CO is not well mixed, not even very high in the troposphere, is not well mixed gas, and many other things. If we move on, in 1984, this paper by Halil and Rasmussen, they describe a trend in CO that they discovered from ground measurements. I think they had 6 years of ground measurements and so on, and they describe an increase in CO. They also very briefly mention seasonality in CO, but they don't get very much into that. The next step would be the flying in the space shuttle of this instrument, MAPS. It flew a couple of times, and actually you could say that this is the first satellite analysis of CO. And in this map, for instance, you can see that they detected differences in CO concentrations higher in equatorial Africa and Southeastern Asia and so on. So that could be considered the first example of satellite CO, but the first real example of satellite CO would start at the very end of 1999 with the launching of MOPITT on the Terra satellite. So here you have MOPITT stands for Measurements of Pollution in the Troposphere. It's an instrument that has been operating since the year 2000, and it's a cooperation between Canada and the States. So the instrument was designed and built in Canada, and here we have a picture of the Canadian team at the late 90s, I guess. This is Jim Drummond, he is the Canadian PI for MOPITT, designed the instrument and so on. And as I said, it's a cooperation because this Canadian instrument flies on the Terra NASA satellite. And here in this picture in the bottom left, you have the recent members of the MOPITT team in the States. We are at NCAR, and we are, our work consists of retrieving CO from the radiances measured by the instrument, validating those measurements, and doing science with the measurements. MOPITT offers the longest global record of CO since 2000 till now, so it's 21 years of record that we have. And very recently, last year, the MOPITT team, as the other teams in the other instrument teams on the Terra satellite, were awarded the PECORA award by NASA and the USGS, and here you have Jim Drummond receiving the award. So a little bit more details about MOPITT. MOPITT is a gas filter correlation radiometer, which makes it a little bit of an outlier. So the main difference is that the instrument has some cells with the target gas inside. In this case, the target gas is CO. So by having the incoming radiance going through those cells, you can pinpoint very precisely the absorption bands for your gas of interest and then focus on those. MOPITT is a unique instrument in the sense that it measures radiance in two spectral bands, in the near infrared and in the thermal infrared. So it performs multispectral measurements of CO. It's the only instrument doing so. Some differences between the measurements from each band. The thermal radiance allows for retrievals both on day and night retrievals over land and ocean, and is mostly sensitive to to CO in the mid troposphere. The near infrared measurements, only retrievals can be done during the day and over land because we are measuring solar reflected radiance. So that only is possible during the day, obviously. And then over water, what happens is that incoming solar radiance is absorbed by the water. So there is no signal that the instrument can measure. So near infrared measurements are sensitive to total column values. And then we have for MOPITT, the multispectral measurements, which have enhanced sensitivity to CO near the surface, which is very important because near the surface is where most of the CO sources reside. With each measurement, with each retrieval, we provide the averaging kernels for that retrieval. And the averaging kernels show the vertical sensitivity of the retrieval to CO. Here on the left, you have ideally, and I should say, MOPITT provides columns in 10 levels. So ideally, for each of these 10 levels, you would have a delta function. So you would have a perfect sensitivity to CO at that level and that level only. But in reality, you have this. So each averaging kernel shows sensitivity at a different level, but it's also sensitive to CO above and below that level. So those are things that need to be considered. And this is true for all instruments measuring CO or measuring other gases. As I said before, the MOPITT data is very carefully validated. So each new version of the data is compared to in situ measurements from airborne profiles. For instance, from NOAA flask campaigns, from HIPPO, ATOM, CONUS AQ, and so on. In some cases, we've also validated the MOPITT retrievals respect to other satellite measurements. In this case, respect to ACE-FTS, and you have an example here on the right. So ACE-FTS is another instrument which measures, among many other species, carbon monoxide on the upper troposphere and stratosphere. And that was very valuable for us because in many cases, airborne vertical profiles do not get very high in the troposphere. So it's a bit harder validating MOPITT retrievals in that, at those altitudes. And for that, ACE-FTS was very, very valuable. And here you have some examples of at the different pressure levels where MOPITT retrieves values, comparisons respect to the NOAA vertical profiles, and you can see that bias values are always in the order of a couple %. Very good results respect to the in situ measurements. To do these comparisons, one has to account for the differences between the observation systems. So in this case, that means you have to account for differences in the MOPITT vertical sensitivity as given by the averaging kernels, and also differences given by the a priori used for the MOPITT in retrievals. So for that, we use the method described by Rogers and Connor, synthesized here with this equation. More about validation. By validating, we learn a lot about the MOPITT dataset. In this case, for instance, in this comparison respect to HIPPO, you have here in the upper right the traces of the location of each vertical profile from the different HIPPO campaigns. So in this comparison, we realized that MOPITT had a latitudinal dependence on water vapor. And here on these two columns for an older MOPITT version, you see that latitudinal dependence as differences in the bias calculated between MOPITT and HIPPO in this case. So you can see that it's clearly a latitudinal effect. So that was identified and corrected in the next MOPITT release, that is the current one, version 8. You can see that latitudinal dependence has very much disappeared or has been improved. So the MOPITT dataset is evolving. Since 2000, it's been improved by comparing to these other in situ measurements, of ground measurements also, other satellites and so on. And each time a new release, a new version is made public, the entire dataset is reprocessed to make sure that it's self-consistent and thus is useful for climate analysis, for analysis of trends and so on. Right now we are working in version 9 of the dataset, and one of the improvements was we improved the cloud detection. In a very recent study comparing MOPITT and TROPOMI retrievals, we realized that we were missing a number of CO retrievals in MOPITT over very polluted regions like China. So in this case, in these maps here on the left of the screen, you have, this would be Beijing up here, you have a TROPOMI CO map and the MOPITT CO map for the same day. And you can see that we are missing a lot of retrievals. All these empty boxes means MOPITT should have retrieved, but it didn't. And if you look at the MODIS visible, you see that the northern half is cloud-free. There are clouds in the south, but not in the north. So what was going on? We went back, analyzed how we were doing the cloud detection, and realized that for cloud detection, and I should say this, MOPITT cannot retrieve in the presence of clouds. So to detect clouds, we use both MOPITT radiances and MODIS radiances. And we were being very strict, and when MODIS saw high aerosols, somehow that was interpreted as cloudy. So by improving that, that cloud detection, we have increased the number of retrievals by a lot. So in here you have the same region, the same day as these other maps in V9, and you can see that the number of retrievals has increased in this case. And looking at only daytime land data has increased by 340%. But in general, globally, we think that by making this tweak, we are going to improve the number of retrievals by around 10–14%, which will make our friends in Canada very happy, because as you can see in these maps here on the right, this change is going to mean a lot more retrievals over Canada. So in here, white means more retrievals and blue less. So you can see that from the older version to the newer version, we are getting a lot more retrievals over this region in Canada. So that's good. And here you have the entire MOPITT dataset since 2000 till last month or so. So each frame is the average for 1 month worth of retrievals. And to me, it's very interesting because it's like I can see the Earth breathing. You can see differences between the northern and southern hemisphere, just like in that 70s paper. You can see that in the southern hemisphere, in general, CO is lower, because in the north we have more population, more industry, more heating, more cars producing CO. And you can see that very clearly here. You can also see this pulsation in the northern hemisphere is more clear. Differences, seasonal differences between winter, where the CO is higher, and summer, where it's lower. Also, you can see these hotspots of CO over the Amazon, Equatorial Africa, Southeast Asia, and so on. And if you're lucky and you catch the end, oh, that was it. So if you look at the end of 2015, you will see a big red blob over Indonesia, which is because of the Indonesian 2015 fires. So and as I said before, the gray regions that you see mostly at very high altitudes in the south and north, those are cloudy regions. And as I said, MOPITT cannot retrieve in the presence of clouds. So let's move on to the next slide, which it also shows the entire MOPITT dataset, but in a more static way. So in this, let me walk you through the meaning of these plots. We have latitude in this axis, time, so 2000 to now, and amount of CO, total CO column. You can see again that difference between northern and southern hemisphere. You can see in the annual seasonality here, going up and down and up and down, and here even more clearly. And then if you look at the colors up here, you see that at the beginning of the mission, you had mostly reds, and now it's mostly yellows. So that's indicating that there is a general decreasing trend in CO. There is less CO now than there was at the beginning of the MOPITT mission. And that's been shown using different data sets and ground measurements and satellite measurements and so on. So that still, if you remember from one of the first slides, I was telling you the first trend analyzed by Halil and Rasmussen. They showed increase in CO, and that's because in the early days, between the 50s and 80s, CO was increasing, and then in the 80s, sort of the trend reversed, and it started going down. Okay, and then, so this is total CO column, and here we have anomalies, CO anomalies. So what I did is I calculated a monthly mean from the whole mission, and then I subtracted that monthly mean from the total column, and this is what you get. Let me move the window here. Okay, so this is what you can see, again, latitude, time, and in this case, anomaly in percent. And the biggest anomaly we've seen in the entire lifetime of MOPITT is in the Indonesian 2015 fires. And very recently, the Australia fires in 2019 and 20 also represent a very big departure from the mean. You can also see some departures in the northern latitudes. Those would be boreal fires in 2005, I believe, and later on. And then in equatorial latitude, you see departure from the mean due to fires in the Amazon, in Africa, and so on. Okay, so let's put MOPITT into perspective. What other instruments on satellites are out there measuring tropospheric CO? And I have to say, I'm just talking about nadir viewing instruments which measure mostly tropospheric CO. So I'm not including in this plot, say, MLS or ACE-FTS, because those are not nadir, and they also measure the upper troposphere, mostly the stratosphere. So going back to MOPITT, you can see that MOPITT operates, as I said before, in the thermal infrared, the near infrared, and multispectral. And then the other instruments that followed, you can see in here, you have the AIRS test, the three EASI A, B, and C that was launched a year ago or so. And then we have no other multispectral instrument. We have Schiamaci that stopped operating a few years ago, and then we have TROPOMI, and very recently this other instrument, TANSO-FTS2. So for a while, TROPOMI and MOPITT were the only instruments measuring in the near infrared, and that's why we had a special interest in analyzing these two with respect to each other. Now we also have TANSO-FTS2. I'm going to talk mostly about MOPITT. As you can see, a lot of MOPITT, some TROPOMI, and some EASI too. So let me give some details on all of them. As I said before, MOPITT is a gas filter correlation radiometer. TROPOMI and EASI are both imaging spectrometers with differences in terms of footprint size and global coverage and so on. So MOPITT offers global coverage every 3 days, TROPOMI every day, and EASI twice a day. And there are 3 EASIs. They use different a priori for the retrievals. So we need to understand those differences to make proper comparisons. And this is an example of a recent comparison between TROPOMI and MOPITT. As I said, we were very interested in understanding how they compare to each other because both measure in the near infrared, and as I said before, until very recently they were the only two measuring in the near infrared, and also because TROPOMI, MOPITT has been operating for 20+ years. But MOPITT is not going to last forever, so we need to make it make sure that global record from MOPITT can be extended into the future with another instrument, such as TROPOMI. So very recently, we completed a comparison between the two data sets, And you can see that they compare, I mean, visually, the retrievals compare very well, both in, you know, the amount of CO each of the two instruments map, and the geographical distributions. So on the left column, you have TROPOMI results for different seasons, and then on the right column, you have the MOPITT equivalent maps. And in a more quantitative comparison here on this panel on the lower right, we did this quantitative comparison for different regions of interest, and we compare TROPOMI to the three MOPITT products, that is to the thermal, near-infrared, and multispectral products. And the result indicated that biases between the two instruments are in the order of 3%, more or less. And that's really good, because the target for TROPOMI was a 15% accuracy. And we are showing that they differ by in the order of a couple of percent. This comparison was performed for land only, and then we did a similar comparison for ocean, for water retrievals. And in this case, we used TROPOMI and ACOM vertical profiles. So you may be thinking by now, TROPOMI measures in the near infrared, so how can it be retrieving over water? Well, it shouldn't, because as I said before, the water is very absorbent, and I mean, there is no reflectance coming back, no solar reflectance coming back from the water, but TROPOMI, what it does is it retrieves over water if there are clouds present. So in this cartoon here, you have a representation of how they do it. They use reference profiles to fill in the vertical column underneath the top of the cloud. So the TROPOMI instrument retrieves over the top, the cloud top, and then they use a reference profile to fill the bottom, and then they provide a total column value. So we were interested in measuring the error introduced by this approximation, and that's why we did this analysis comparing TROPOMI and ACOM vertical profiles. So ACOM, you have here showing the location of the ACOM vertical profiles that we use. Each dot is one profile, and this is an example of an ACOM profile, so very detailed in the vertical. And the results were really encouraging. So by applying this approach of filling under the cloud with a reference profile, the errors are in the order of 3% or so. So here in the top, you should see the little circles from the ACOM vertical profile values on top of the TROPOMI map for the same time period. And it's a good thing that you don't see the circles very well, because that means that both ended retrieving very similar values. And in here you have a more quantitative representation of their similarity. This would be before applying the TROPOMI averaging kernels and after applying those averaging kernels to make the comparison more apples to apples. So, and you can see that biases in this case were around 3%, which is very good. And another intercomparison in here, what you can see is a TROPOMI movie with CO retrieved last year during the Siberian fires. So you can see the plumes, big CO plumes starting in Siberia over here and moving over the Pacific and getting to North America. And here on the right, you have the WACAM model results for the same period. So while these fires were taking place, there was a campaign, FireX AQ campaign from NOAA and NASA, with a couple of planes chasing fires, local fires in Washington State and Oregon and so on. And then once we figured out that this fire was going on in Alaska, they started chasing the plume from that fire. So in these airborne campaigns, they use satellite data and models to know where to go, where to send the planes to chase, in this case, fire plumes. So it's quite remarkable, I think, how well the model and the TROPOMI data agree in this case. And even though the colors are slightly different, you can see that the shape, the location, the size of the plumes are remarkably similar. So TROPOMI is great because it gives you this global view of total column. And here is another view of the same TROPOMI data, different projection, but you can see the plumes starting over Siberia and then moving over the Pacific and around and ending up on North America. So TROPOMI is great to give you that synoptic view, global view, daily CO. MOPITT has the ability to see in the vertical. So in this case, here I'm showing MOPITT CO profiles in red, measured over Siberia, where the fires were taking place. And you can see the anomaly, the high CO is very near the surface. And then on the same day, looking at CO over Vancouver Island on the west of Canada, you can see this MOPITT measured elevated CO, but in this case, it was at around 9 kilometers high. So MOPITT has that ability to see the location of CO in the vertical, so you can tell a local source from transported CO in this case. It's a very valuable capability. So an example of an analysis of a large fire in North America that took place in 2005. In this case, Gabby Pfister, she analyzed MOPITT data for 2004, sorry, fires in 2004, MOPITT data and model results from Mozart. So she was able to measure the amount of emissions produced in these fires. And here you have results of that comparison in the lower right. And you can see that the model, after ingesting the MOPITT data, detected these large amounts of CO, large plumes. And she calculated, I think it was 30 teragrams emitted during these fires, I think. Anyway, so she calculated the size of the emissions, and then she went to say these emissions produced from this fire are equal, the amount of CO emitted is equal to the CO emitted by the whole United States by anthropogenic emissions during the same period of time. And here there is a comparison between the model results and airborne results from index NA that was taking place at the same time. So you can see the plume here as seen by the airplane and as seen by the modeling results. So here we are quantifying emissions from the satellite data. Sorry, sometimes I have trouble moving between slides. This is one of these cases. There you go. Another study case involving fires, in this case over the Amazon. In this study, Bloom et al. Look at area burned, shown here in gray, as shown by MODIS imagery. And they focus on 2 years of very strong droughts, 2007 and 2010. So you can see that the amount of surface area burned is much larger in these 2 years compared to the years before and after. In green, you have CO emissions as shown by MOPITT in dark green and TESS in light green. And you can see that the emissions in 2010 were lower than one would expect looking at the emissions in 2007. So there is not a one-to-one correspondence between area burned and amount of CO produced, even though it's the same region. Why is it so? In this study, they figured out that the reason was that because of the repeated burning seasons, vegetation, it just doesn't is not as dense after having been through these fires year after year. So you may have a large area being affected by fire, but the CO will not be so high if the vegetation is not dense, because it's not so healthy anymore after going through fire so many times. Okay, so now we move to the largest CO event observed by MOPITT in all its life, the Indonesian 2015 fires. Start by saying that those fires coincided with the largest El Nino event during MOPITT's lifetime, which is shown in here. So MOPITT started operating in 2000, unfortunately, right after another very big event, but since 2000, this one was the biggest in 2015. So here in the upper right, you have, let me go through this one a little bit carefully. So each line shows daily CO from MOPITT calculated for a latitudinal band between 15 south and 15 north for all longitudes. So it's an average. And you can see that most years, shown in black, follow the same pattern. Now we go to 2015 and it starts pretty much the same. And then during the fires, the fires are shown in the dark box here, during this time, CO is much, much higher. It's like 50% higher than what was normal before and after. And then if you follow to the next year in green, you say that for 2016, the CO it's still higher than it used to be in the rest of the years. And it's so until pretty much April. I have to say, this is for CO at 300 hectopascals, so pretty high in the troposphere. And that's an issue. This persistence of the CO it's something that it's been in the back of my head since 2015. And someday I hope someone will have the chance to explain why the elevated CO, because in theory, after a couple of months, that CO should not be high anymore. So is it that there was so much CO that there was not enough OH to consume it, or were there other species emitted in the fire that resulted in extra CO, or maybe CO from other fires? It's an open question. In any case, the emissions during the fire were much higher than usual, and you can see here in this map, you can see that the surface values were around 1300 ppb, which is really high for surface values. You can see that rainfall during the month of the fires had been extremely low. And in this analysis by Field et al., they show that when you go past a certain threshold in terms of lack of rain, the fire effects are not linear anymore. So in this case, in the Indonesian 2015 fires, they went below 4 millimeters per day of rain. And you can see how, in this case, CO emissions just shooted, yet it went non-linear. And what I show in this panel, in this paper in Field et al., they did for other species, for CO from other satellites, from other species, and for everything, they saw the same response. So it's not like if it's a little bit drier, you get a little bit more CO. After a certain point, it goes non-linear. So in this paper, they made the point that the authorities should warn, the people not to burn their fields if the year was particularly dry. So that's that. Here in this paper, Zhang et al. Calculated emissions for different years and different fires, and for these specific fires in Indonesia 2015, they calculated around 92 teragrams of CO being emitted. And now we move to the Australian fires in 2019 and 20. This is a movie made from TROPOMI CO. You can see the plumes generating in southeastern Australia and then producing large plumes that move all around the southern hemisphere. With MOPITT, we can see how that CO was distributed vertically. So again, this is a similar plot to what I showed for Indonesia. You have for a year the daily means from each MOPITT year. Most of them are shown in black, and then the year of the fire, when the fire started, 2019, is shown in red, and this would be total column and different altitude levels, 300, 200, and 100 hectopascals. So you can see that during the fires, CO starts to go up, and then the next year you can see this huge anomaly in CO in total column, and you can see it even at 100 hectopascals, which is way high in the troposphere. Oops, I went a little bit too fast. So let's just move to the next one. And not only it went high in the troposphere, it went into the stratosphere, as shown by, in this case, we have Calypso Calliope data here, and this is the location. So we are looking at a region in the middle of the Pacific, east of Australia. So if we look at CO, in this case from YASI in blue, and from MLS. MLS is another instrument that measures different gas species in the upper troposphere and in the stratosphere. So if we look at those over the fires, you see very high values near the surface, but higher up things look normal. Now, if we go the same day in the middle of the Pacific, you see values that are not very high at all. And then a couple of days later, in this same region, a couple of days later on the same region in the middle of the Pacific, you have this. So both YASI and MLS see really high CO. MLS sees a peak around 15 kilometers, which according to the Calliope data, 15 kilometers, you have this, this layer of aerosols way over the tropopause. The tropopause is showing the black line here. So you have, in this case, an example of a fire producing an stratospheric injection due to pyrocumulonimbus activity. So the conditions are such that the emissions from the fire go really high all the way, in this case, to the stratosphere. And this is, it has very strong implications for climate, because once you send aerosols and certain gas species into the stratosphere, those have the capacity to change the radiative properties of the stratosphere. So, and even more recently, here we have a map from YASI data provided by Cathy Clairvaux from the YASI, she's the YASI PI. And here you can see the emissions from this summer, from just a couple of weeks ago, from mostly fires in California, and the CO emissions affecting the entire states and traveling across the Atlantic and reaching Europe, and it went around and circumnavigated the globe. Some people say a couple of times, these emissions from these fires here. Okay, so let's move on. Let's leave fires behind. And here's an example of something that we did with MOPITT, which was MOPITT and YASI, the first satellite identification of volcanic CO. Any volcanologist will tell you that volcanoes emit CO, but that's something that had never been measured from satellite. And here in these examples, we studied some eruptions that took place in Iceland in 2010 and 11, and we were able to identify CO emitted from the volcanoes. Because we used data from two very different instruments, MOPITT and YASI, we were certain that we were making the proper identification, and we also use aerosol data and SO2 data from OMI. And we estimated that the CO emitted by volcanism globally is around 5.5 teragrams per year, which is not tremendous, but it's non-negligible either. And now we move to a different topic, which is satellite detection of CO emitted in cities. In this example, we have the first identification of urban CO made from satellite by Cathy Clairvaux using MOPITT, and she analyzed data over several big cities, and averaging data along a couple of years, she was able to show an anomaly of CO associated with these big cities. You have Tehran, Jakarta, Los Angeles, and so on. And here on the right, there is the case of Beijing, MOPITT CO shown in here, versus population density, and versus CO from an inventory. And you can see that the correlation is very nice. So, but she had to average data acquired along a long period of time. In a subsequent study, Matthew Pommier was able to show differences in CO emissions along time. And he did this analysis with MOPITT again, and look at the different examples. This is for Baghdad. And with a very clever technique, he was able to calculate total column values emitted from activities in this city, and to show that between 2002, 2003, shown in blue, and 2004 and 2008 was a noticeable decrease in emissions from this city. Of course, now you can do that in one day. With TROPOMI, with a single pass, you can identify emissions from cities. And here are some examples, cities in northern Italy, in Egypt and Saudi Arabia, Mexico City, and this is over Iran, I think, yeah, Iran. So, and then focusing on Mexico, in this panel here on the upper right, you can see in blue, ground measurements using an FTIR of CO, daily measurements, and then in red you have the TROPOMI measurements, and they agree beautifully. You get to detect emissions without any averaging, and then when you compare to ground measurements, they agree really nicely. So that's a great advancement. Helen Warden, she performed this really nice analysis a few years ago using MOPITT data, where she studied the effects of controlling traffic during the Beijing 2008 Olympics. So during the length of the Olympics, people couldn't drive their cars, and I think that the industries either diminished their activity or stopped altogether. And from satellite, using the multispectral MOPITT retrieval, which is sensitive to surface emissions, she was able to detect changes due to these controls in traffic and so on, and then compare to model results from WRF-Chem, and measure the difference in emissions that these traffic restrictions produced. And the result was very encouraging, because she, from the CO, from the change in CO, she was able to extrapolate to change in CO2. And she concluded that just by traffic restrictions in big cities, it could be possible to decrease CO2 emissions enough to reach the goal of not going 2 degrees C higher in temperature by 2100, by year 2100. So just by controlling traffic emissions. And then another experiment that is being forced upon us is the effects of lockdowns due to the COVID-19 pandemic. So early on, we performed this analysis looking at CO from MOPITT in the top panels and from TROPOMI in the bottom panels. So this shows you the CO between February and March in 2019, so last year, and then the same period of time this year. And you can see right away that the amount of CO has gone down. This is China, I should say. We're looking at the China here. So both instruments agree very well in the amount of CO, the amount of decrease in CO, and here you can see that difference. In blue, it means that CO has decreased. And you can see that it's shown in the MOPITT and in the TROPOMI maps. And here you see some increase in CO over Thailand, here and here, but those are due to large fires that were going on at the same time. So this is biomass burning produced increase in CO, anthropogenic emissions went down during the lockdown. And let's look at CO trends with MOPITT and other instruments. So in these graphics, and this is from a work which is currently under review by Rebecca Buchholz. It's a very nice work where she is looking at CO as measured from all satellite instruments operating in the thermal infrared. So you have MOPITT, YASI A and B, AIRS, TESS, and CRIS. And they agree very nicely. And then when you look into the trends, and these are trends separated for the northern hemisphere and southern hemisphere, you can quantify this trend, which is obviously decreasing, and it's around 0.6 or 0.4 for the northern and southern hemisphere. And those trends were only calculated for MOPITT and AIRS because the other instruments either were too short to allow for calculation of trends, or they were not self-consistent enough to allow for a proper trend to be calculated. And I think I mentioned already that initially in the 50s, CO was going up, but then since the 80s, it started going down. And in a similar analysis up to 2013, those trends were stronger. So CO was decreasing by around 1% per year. And now it's still decreasing, but not so much. Here you have another map from the same analysis by Rebecca Buchholz. And this is trend minus global trend. So it shows you local trends, if you would. You can see that mostly in the northern hemisphere, there is a strong decrease in CO and also in the Amazon. And remember that this study goes till 2018, I believe. While in Equatorial Africa and India, CO is actually increasing. So we can go one step forward and say, okay, so now we know that CO is decreasing, but why is it decreasing? Is it because there is less biomass burning or less human emissions, or what is it? And you can remember, you probably remember this from one of the early slides where we have the relative importance of biomass burning, human emissions, anthropogenic emissions, oxidation and vegetation. So in this really nice study, Yang et al., they modeled emissions using MOPITT and using the GeoSchem model. So first of all, they asked themselves, so is it that CO is going down because changes in OH? Is there more OH and thus it destroys more CO, or is it because CO is changing? And they figure out, looking at methyl chloroform, that OH is not changing, so the cause for the trend is CO emissions. And then they were able to calculate emissions from different sources, and they figure out that anthropogenic emissions are decreasing very dramatically in the USA, China, and less in Europe, but they're increasing over India. And biomass burning is mostly decreasing in the boreal regions and in the Amazon. They didn't see a clear trend over Africa, and the trend over Indonesia was increasing, but it was probably because of the 2015 fires. So that's a big outlier. So it's a bit more uncertain. And trends in emissions from oxidation were not clear from the results from this study.
Sarah, it's 1:01, so hopefully we can grab a couple of minutes for questions.
Oh, that's awful. I'm well behind, but yeah. Okay, well, let me go super quickly. These are some examples of CO satellite measurements used in assimilation cases for air quality, for climate. The future is geostationary satellite called GeoCarb. MOPITT, unfortunately, is not going to last much more, a couple of years longer, and we are going to be out of the constellation and not working anymore in this wonderful data set. But hopefully, at some point, we'll be able to simulate multispectral retrievals using data from CRIS and TROPOMI with extra sensitivity at emissions near the surface. Give a shout to this conference from the Amigo group, who are interested in using satellite data to improve emission inventories. And I leave you with this map of CO from TROPOMI over the States from a couple of weeks ago that you can see at the ACOM Worldview, which is a wonderful tool, publicly available. And then just say thank you to all of these wonderful teams, in particular to the MOPITT NCAR team and to our friends in Canada. And many, many thanks to you.
Okay, thank you so much, Dr. Alonso. So we've got hopefully a couple of minutes for questions if folks can stay on. If anybody would like to ask a question, please use the raise hand in the participants tab, and we will open you up. Okay, so I guess I've got a quick question. You mentioned that in the next little while, MOPITT will be dropping its descending node past the acceptable time. I was wondering what impacts the shift in the orbit would have and why that would mean that it's not usable data anymore.
Well, a couple of years ago, when we knew that the MOPITT mission was going to end because of lack of fuel, that's the only reason, with all the other instruments in Terra, we did some calculations and we figured out that MOPITT is not going to be affected at all by the change in altitude of the orbit. And actually, we are sort of looking forward to that change because that will mean that the passing time is going to be different. Instead of being, I think it's 10:30 now, it will be decreasing until at the end it's going to be 8:30. So you're getting closer to, say, rush hour, which opens up many possibilities for analysis of urban emissions and so on. So it doesn't mean that the science is not going to be valuable, quite the opposite, because now we have new opportunities open to us. We were stuck at a certain passing time, a certain altitude, and now we are going to get a chance to look at things differently. So we are hoping that until 2026, we are kept on, so we can still acquire data and retrieve from those data. So that's very much our hope. It's not clear yet. That's a decision that is now in NASA's hands.
Wow. So with the descending node so early, are you still able to get like sufficient sunlight, a good solar zenith angle in order to collect data?
Yes, and also remember that we are multispectral, so the thermal wouldn't care, and the near infrared, as I said, is 8:30, so it's not that shouldn't be a problem.
Oh, that's great.
Also, another good point is that and this is relevant also for other instruments. I mean, it's not just MOPITT, it's all the instruments on Terra which are going to end their missions, but it's also very interesting to have it change in passing time for instruments like the MODIS, because MODIS is used very much to monitor fires. And it's very interesting to have an early picture of fires so the local agencies can plan ahead and say, okay, it's early in the morning and we have these fires here, so we should start moving now. So having an earlier passing time for, say, MODIS, for fire counts and so on, it's also a very, very interesting option.
Oh, that's great. Okay, I'd like to thank